the more heat they beamed into a spherical tokamak, a magnetic facility designed to reproduce the fusion energy that powers the Sun and stars, the less the central temperature increased. Big mystery. Normally, the more beam power you put in, the higher the temperature gets, said Stephen Jardine, head of the Theory and Computational Science group that performed the calculations, and lead author of a proposed explanation published in Physical Review Letters. So this was a big mystery. Why does this happen? Solving the mystery could contribute to efforts around the world to create and control fusion on Earth to produce a virtually inexhaustible source of safe, clean and carbon-free energy to generate electricity while fighting climate change. This mechanism might be general in spherical tokamaks, he said, and the possible destruction of surfaces must be taken into account when future spherical tokamaks are planned. And he has been invited to present his findings to the annual meeting of the American Physical Society Division of Plasma Physics, APSDPP, in October, where early career scientists could be recruited to take up the issue and flesh out the details of the proposed mechanism. Increasing the power also raises pressure in the plasma to the point where the plasma becomes unstable and the plasma motion flattens out the temperature, they found. These simulations likely explain an experimental observation made over 12 years ago, Jardine said. The results indicate that when designing and operating spherical tokamak experiments, care must be taken to ensure that the plasma pressure does not exceed certain critical values at certain locations in the facility, he said. The researchers simulated past experiments on the National Spherical Torus Experiment, NSTX, the flagship fusion facility at PPPL that has since been upgraded and where the puzzling plasma behavior had been observed. The results largely paralleled those found on the NSTX experiments. Through NSTX we got the data, and through a DOE program called SciDAC, Scientific Discovery Through Advanced Computing, we developed the computer code that we used, Jardine said. Physicist and co-author Nate Ferraro of PPPL said, the SciDAC program was absolutely instrumental in developing the code. The discovered mechanism caused heightened pressure at certain locations to break up the nested magnetic surfaces formed by the magnetic fields that wrap A. So what we now think is that when raising the injected beam power you're also increasing the plasma pressure, and you get to a certain point where the pressure starts destroying the magnetic surfaces near the center of the tokamak, Jardine said, and that's why the temperature stops going up. Sup. 2022, July 13. Scientists propose solution to a long puzzling fusion problem. Science Daily. Retrieved July 13, 2022 from ift.tt/mkzdhd2 DOE, Princeton Plasma Physics Laboratory. Thanks for watching. Please subscribe my channel for more videos.